So good afternoon. I'll be presenting BuildRoot, a tool that helps building embedded Linux systems in an easy way, and also probably one of the projects that is the ugliest logo possible. But that's not really the point. Before we get started, a quick poll. Who in the room is either working or playing with embedded Linux? Yeah, so a good number of people, like more than half of the room. Okay, great. So first, who am I? In a quick few words, I'm the CTO and embedded Linux engineer in a company called Free Electrons. We do embedded Linux stuff, both development and consulting and training. We have a strong open source focus, so we contribute to the Linux kernel, for example, to BuildRoot. And we also release all our training materials under a Creative Commons license, so we have lots of embedded Linux and Linux kernel training course material freely available for everyone to download. I am an open source contributor. I contribute to the Linux kernel, especially on the ARM support for certain processors, namely the ones from Marvell. And I'm also a major contributor to BuildRoot with, in fact, not 1600 but 1900 patches contributed since the last few years. And I come from Toulouse in France, so quite far away, and you've probably noticed my terrible accent. So embedded, these days when people say embedded, usually they think something like that, like phones, tablets, consumer-grade devices. And those devices, they typically have very powerful CPUs, lots of RAM, lots of storage, a full-feature general-purpose operating system, usually Android, but it can be something else, but something with like many applications that you can install, remove, upgrade, and so on. So really a complete desktop operating system. But in fact, embedded is much more than just the devices that you have in your pocket. We have embedded systems in like laser cutting machines, point-of-sale terminals, agricultural machines, windmills, and many other systems that you may never have heard of. And those systems are much more application specific, so they need a more custom Linux system that may need to boot fast or meet some real-time deadlines or have other types of constraints. They usually have a lot less powerful CPUs. Typically, like in a few hundreds of megahertz is quite common in those systems. They may use like specialized CPU architectures, so there's much more than x86 and ARM in the embedded world. MIPS for PC, of course, but also like Blackfin, Microblaze, Nios, and other bizarre architectures you've probably never heard of. Those systems have also less RAM, less storage, and a long lifetime and maintenance period. So the constraints are quite different than the ones that we have in consumer-grade devices such as phones and tablets. And so the way we're going to create the Linux systems for those two types of embedded systems might be a little bit different, as we're going to see. So to build an embedded Linux system to like integrate all the different components that make a Linux system, the init system, the graphical stack, and the network processes, and so on, there are different solutions that are available. The first thing that every one of us do is use binary Linux distributions, Debian, Ubuntu, or more specialized one like Raspbian for Raspberry Pi or other distributions. So those are pre-built. So what you get are binaries that have been compiled by other people. So the good thing is that it's readily available, it's easy to install, easy to use, but it's quite large, it's not available for all architectures. It's not necessarily very easy to customize. So of course you can install and remove packages, but if you want to like slightly adjust the config of one package or rebuild the entire thing with different compiler options, it's a little bit tricky. And it generally requires native compilation. So if any one of you have tried to build a Linux kernel on a Raspberry Pi, it takes a long, long while. So native compilation is certainly nice for some things, but for some other things it's not so nice. So the other approach is the other side of the spectrum is to build everything manually. So from scratch, you take the source code for every component in your system, take the tarball, configure it, build it, install it, and do all of that stuff. But it's quite hard because you are going to face cross-compilation issues. You'll have to face the resolution of the dependency tree. And in the open source world, we reuse a lot of things, so there are many libraries. It's not reproducible unless you take very clear notes of what you've done, and you don't benefit from other people's work. So there's kind of an intermediate solution that sits in between. And of course, as you might have guessed, BuildRoot fits in that intermediate solution. This intermediate solution is the usage of tools that automate the process of building a Linux system from scratch, from source code, all the way to a completely working system. So since we build from source, we can customize as we want. We can build very small and flexible systems, so we can just have what we need inside the system and nothing more. It makes the process reproducible because we have a tool instead of just a bunch of command lines that we run. The tool handles the cross-compilation and dependency issues. It's visually available for all architectures. We're going to see which ones Buildroot support. But of course, it's one tool to learn, and you have to, well, spend some time waiting for the build to finish, but at least you're not involved into that, so you can drink some coffee or other nice drinks while the build is going on. So the principle of those tools is, there are many tools in this, well, area, but the principle of all of those tools is more or less the same. Basically, they take some source code, either from open source components or in-house components, from their Git trees or tarbles on the web. And they are going to produce at the end a root file system image that contains all your application and libraries and init scripts and config files and so on. Possibly a kernel image, a bootloader image, and a cross-compilation toolchain. And you're going to feed into this tool a configuration that says, for my system, I'm going to build it for ARM, and I want this graphical library to be inside, and this networking application, and so on and so on. So as I said, you build from source, so you have lots of flexibility. You can adjust whatever configuration option for each individual component as you want. Since we're cross-compiling everything, we are leveraging the power of our fast desktop and server machines. So you can like have a big Intel machine to do all your cross-compilation, which allows you to build a kernel for your Raspberry Pi in just a few minutes instead of a few hours if you do native compilation on the target. And those tools have recipes for building components, so it makes it easy. Instead of having to worry about how to compile x.org, you just select an option and it's gonna do it for you because the tool knows how to build x.org. So there's a wide range of tools available to do that. Yocto and OpenEmbedded, PTXDist, Buildroot, LTIB, OpenBricks, OpenWRT, and much more that I've probably forgot. But from what I can see, but of course I have a biased opinion here, I think two solutions are really emerging as the most popular ones. On one side, there is Yocto and OpenEmbedded. What those tools allow is to build a complete Linux distribution with binary packages. So it produces like your own custom Debian for you. And then from this set of packages, you can create embedded Linux systems that are able to upgrade, install, remove applications through binary packages as you normally do in a binary distribution. Those tools are very powerful, but they are somewhat complex and have a quite steep learning curve. So if you want to invest quite some time, they are certainly nice. Buildroot is kind of the opposite side of the spectrum. It simply builds a root file system image. There's no binary packages. You can't like install, upgrade, remove things. If you want to change something, you have to go back into the tool, adjust your configuration, and recreate a new root file system image, which is perfectly fine for most of the embedded Linux systems that are used in the industrial space. And it's also a tool that's much, much simpler to use, understand, and modify, as we're going to see throughout the presentation. So in just a few words, what are the main characteristics of Buildroot? It's a tool that can build a toolchain, a root file system, a kernel, a bootloader. It's an embedded Linux build system. It's easy to configure because it uses a mini-config, xconfig, nconfig, gconfig interface, just like the Linux kernel itself. So if you've ever built a Linux kernel, you already know the configuration interface for Buildroot. It's fast. You can build a simple root file system in just a few minutes, so you don't have to wait for hours. It's very easy to understand because it's written in Make and it has pretty good documentation. Of course, it could be better, but we have good documentation, I believe. The default file system that it builds, it weighs 2 megabytes. So it's, when I say small, I really mean small. So it just contains small C library, and which is UClipc and BusyBox, and that's all. And then you can add more stuff on top of it, but at least you start with something small. It has more than 1,000 packages available, so you can just select things and you don't have to worry about how to actually compile it. And there are many architectures supported. It uses well-known technologies. As I've said, it's based on Make, so it's entirely written in Make files. And it uses kconfig for the configuration interface. So any like kernel developer or Linux developer in general knows those technology already. It's also a vendor-neutral tool, so it's not like one single company behind the tool doing the development or driving the directions. It's really an open source community doing it. And it's probably the oldest build system still in activity. It's been created in 2001, actually, so it's quite old. And the community is very active, regular releases. I'm going to talk more about that a bit later. So who's using Buildroot? Google is using Buildroot. They do Google Fiber in the US, and the boxes, they have an embedded Linux system, and they use Buildroot to produce it. Barco is a, international company doing visualization systems. Rockwell Collins, they work in the defense and aerospace industry, and they also use Buildroot, and they're even contributing to it. And we have many more. I just took like 3 examples. We also have a lot of processor vendors that are using Buildroot as their BSP, so they provide their customers a Buildroot that is specifically configured for their own architectures. So like Analog Devices for Blackfin, Imagination Technologies for MIPS, Marvell, Atmel for ARM, and there are several others. And also many hobbyists that do embedded Linux development on boards like Raspberry Pi or BeagleBone Black and so on find Buildroot really nice because it's easy and simple. So how do you get started with Buildroot? Well, you just grab it from the Git repo. Well, there are stable releases, of course, but it's probably easier with the Git repo. And then you fire make menu-config, and you have the well-known menu-config interface to configure all the different aspects of the embedded Linux system you're going to produce. So I'm going to go through pretty quickly on the different configuration aspects that are available. So first you need to select the architecture, and as you can see there are several of them that are supported, including like ARM64 or SuperH or Nios 2 that are quite weird architectures, and all the more common ones are available. And then in this part you can also select more specific options specific to each architecture, like the type of processor and what type of floating point strategy and so on. There are some like build options where Buildroot is going to download the tarbles, how many things you do in parallel, whether you want to use Ccache and that kind of things. Another very important part is the toolchain, which cross-compiler you're going to use. And you have 2 options here. Either Buildroot can build its own cross-compiler, in which case it's going to build GCC and the C library and the bin utils and so on, and it supports uselibc, glibc, and eglibc as the different C libraries. Or the other option is to use what we call an external toolchain, where you already have a cross-compiler that's known to work really well for your architecture, and you can just tell Buildroot to use it. And the other advantage of using an external toolchain is that you don't have to pay the price of building the toolchain, which takes quite a while. So you save like maybe 20 minutes to 30 minutes of build time if you use an existing toolchain. Then you have a way of doing some system-wide configuration, like which init system you want to use, whether you want to use BusyBox as the init system, which is the default because that's very small, or if you want to use systemd or a more traditional system5 init. You can select how you want to handle /dev, like whether you want to use udev or devtmpfs. There are various solutions, and other system-wide configuration options like what's the root password and whether you want a shell to run on some serial port and so on. Then you can define which kernel should be built, like which version, whether it's come from a Git repository or whether there are patches, which configuration should be applied, so it can be given as a file or as a devconfig. And we have support for the 2 probably most popular real-time extensions like RTAI and Xenomai, so it can be integrated easily in Buildroot as well. And then the most important part is definitely the target packages, what you're going to put in your root file system. That's where the highest value of the embedded Linux build systems is. And that's where we have more than 1,000 packages. So we have things like Qt4, 5, x.org, GTK, EFL. So that means that by simply selecting an option in the menu config, you can get Qt5 built for your target platform without having to worry on how you actually need to configure it and compile it and how to install all the stuff. We have things like GStreamer, FFmpeg, many interpreted languages, many networking applications. We have, since Google Summer of Code last summer, we have OpenGL support for various platforms and many libraries and utilities. There are too many to name all of them, obviously. Another part of the configuration is which file system format you want to generate. So we support things like ext2, 3.4, of course, but also more embedded specific file systems like UBIFS or GFFS2 for flashes, or SquashFS for read-only file system. So this morning someone was asking during the lightning talk, I'm having like file system corruptions on Raspberry Pi for some museum exhibitions and so on. So typically a good answer would be do something with SquashFS, and BuildRoot can by default generate a root file system that remains read-only. So if it's read-only, obviously you kind of limit the occurrence of file system corruptions. I'm going in the wrong directions. You can also build bootloaders. So depending on which architectures you use, the bootloader will be different, but we support grab, Linux, U-boot, Bearbox, and a bunch of platform-specific bootloaders. So really you define all the aspects of your embedded Linux system. There are also the possibility of building some native tools that are useful for development, but it's kind of a side thing. Here is an example configuration. So just like the Linux kernel, the configuration gets saved in a file named .config, which is just a text file that says for each option what's the value. So here is the configuration for the Raspberry Pi. So it's going to build a kernel for ARM platform with an external toolchain. It's going to include the Raspberry Pi firmware and userland, proprietary binaries, the I2C tools, and then the TV head-end streaming server, and the Dropbear SSH server, and the Light HTTPD web server. And just with this configuration, it's going to produce you directly an image that you can use on your Raspberry Pi. So to start the build, you run make, and that's the point where you drink 1 or 2 or 3 cups of coffee or tea, depending on your taste. And at the end of this process, in the output images directory, that's where the real stuff gets put at the end of the build process. You have the root file system image. So here I've selected both a tarball format and a UBI format, which is for some embedded system. You have the kernel image and the U-boot bootloader image. Of course, it completely depends on your configuration, but that's really what needs to be flashed or installed to your target system, like pushed to your SD card or flashed in some way to your embedded Linux platform. I'm going in the wrong direction again. So if you want to have a look at the build output of what BuildRoot generates, it all goes in the output directory by default, but that can be changed using O equal to do out of tree build, exactly like the kernel. And output contains output build, where BuildRoot is going to extract the source code for each and every component it's going to build. So for like GCC, BuzzyBox, and Light HTTPD, and so on. And that's where it's going to build each of them. Output host is where BuildRoot installs all the host utilities. So like when you build things for the target, you need things for the host. For example, the cross compiler, but there are many other tools that you will need, so it's going to install them here. In output host user, the tuple of your architecture, so typically something like ARM, unknown, Linux, like GNU ABI, sysroot. It's where BuildRoot is going to install all the headers and the libraries that have been built for the target. And it allows the cross compiler to find them and build more libraries and more applications on top of the libraries that have been built previously. That's what allows to, solve the dependency tree. Output target, it's what contains almost the target root file system. So why almost? It's because since BuildRoot does not run as root, we cannot really create completely the root file system. The permissions and the file ownership are wrong, but we fix that up later when we create the real images, so that this directory cannot be used directly as a root file system, but it's really almost like it. And then, as I said, output images where you find the final images that are interesting. So the build process is pretty simple. Of course, if you go into the details, it's a bit more complicated, but the overall overview of the build process is quite simple. BuildRoot starts by copying what we call the root file system skeleton to the target directory. So the root file system skeleton is just like an empty root file system. It is just like etc and bin and lib, completely empty, just a bunch of config files in etc, and that's pretty much it. Then it takes care of the cross-compilation toolchain, and as I said, there are two solutions: either let BuildRoot build your toolchain or use an external toolchain, and in both cases, BuildRoot takes care of what's needed to either build it or like import the already existing toolchain. And then for each of the selected packages, it's going to first take care of its dependencies. So it's going to do this third step recursively for each of the packages. And for each of them, it's going to download the source code and potentially some patches, extract them, apply the patches, configure it, build the components, and install it. And it's going to install it in different locations depending on the specific component you're building. For target application and libraries, they are obviously going to be installed in output/target, so they end up in your root file system and show up in your target platform at the end. The target libraries also are installed in the sysroot so that they get seen by the cross-compiler when you build more application and more libraries, as I was saying. And in output host, that's where we install all the native libraries and applications, like the cross-compiler itself, but also more things like, I don't know, if you need Flex or Bison to build something, they are going to be installed in there. And finally, once that process is done for all the packages that you've selected, taking care of the dependencies and ordering the build properly, it's going to generate the root file system image and your system is ready to use. So here are two real-world examples of projects that I've done using Buildroot. So one of them was for a company making a device based on an ARM Atmel CPU, which was like 200 or 400 megahertz maybe, like 64 megs of RAM, so pretty limited. And in this device, it was used to like track things going on using GPS, RFID readers, GSM modem, Ethernet, and USB. And in the system, we had like we used a glibc toolchain pre-built, so we didn't have to spend time building it. A Linux kernel, BusyBox for the basic stuff, an SSH server and clients. We had the basic Qt library, not the graphical part, but all the core. And some more components like PPPD for GSM interaction and some special RFID library and other things. The Qt application that was really making the system do whatever it was designed for. And we generated a GFFS2 file system. And the file system was 11 megabytes in size with all these components. And it was actually using glibc, which could be made a little bit smaller if we used uselibc. And to build all that stuff, it was taking 10 minutes on a quad-core i7 build machine, which isn't like, it's good, but it's not exceptionally, enormous in terms of CPU power. Another one is a system that's based on x86, which is used for a vehicle navigation system that mainly runs an OpenGL application showing what's going on in the area. So here we used a glibc toolchain that was prepared with a tool called crosstoolng, which is specialized in the creation of cross-compilation toolchain, so that again, Buildroot doesn't have to spend the time to rebuild the toolchain over and over again. We used the grub bootloader, Linux kernel obviously, and BusyBox. It's kind of always the same thing. We had a large part of the x.org stack. And there was one interesting thing here is that this project was using an ATI card, which is proprietary driver for the OpenGL implementation. And those drivers were dependent on a very specific version of the kernel and a very specific version of x.org. And thanks to the fact that we're building everything from source, it's pretty easy to select very precisely which version of each component you want in the system, which sometimes is a little bit more complicated when you have binary distributions. Of course, you could use like an older Debian, but then everything is older. While here we can have everything recent except just the very specific libraries or version of the x.org server. So the flexibility of building from source is sometimes very useful. And then we had a bunch of libraries like ASA stuff and V4L and so on, and the OpenGL application. And in the end, the file system was 95 megabytes, which is quite huge. But if you look at what's made this size, there's actually 10 megs of app and 45 megs of the ATI driver. I don't know what they do exactly in their drivers and OpenGL implementation, but it's crazy. And this system was taking 27 minutes to build on the same build server quad-core i7. So it's pretty reasonable. I mean, of course, you need to drink a little bit of coffee, but not too much. So besides selecting the different packages, there are different ways you can customize the build because, well, packages are interesting, obviously, but possibly you need to add more configuration files or adjust things in the root file system, and there are different ways to do that. Buildroot provides what we call post-build and post-image scripts. So in the build process, which I can basically go back here, you can ask Buildroot to execute a script before point 4 and after point 4, which is respectively post-build and post-image. So before the image is created, you can like add more files in the root file system, adjust configuration files, remove things, and do whatever customization you want. And after the images are created, you can maybe bundle them together to create a firmware image update that will be pushed to your customers or whatever. That's one way. And we have another way which is called the root file system overlay. It's kind of related. It's basically you tell build root, here is a directory that contains stuff, and once the build is done, just take this stuff and copy it inside the root file system. So you can put all your custom config files, custom init scripts, custom maybe even application or whatever in there, and it's going to be part of the build and taken by build root into the root file system. And the last way you can use to customize the build is by adding your own packages, either to package open source components that are not yet handled in build root, or your own in-house components because you need to integrate your own libraries, your own applications into the build. And so I'm going to show quickly what it looks like to create a new package in build root. So first of all, you have to make your package appear in the menu config interface. And here, thanks to the fact that we use the exact same code base as the kernel for the kconfig base, well, it's exactly the same as defining configuration options inside the kernel. So any person having a little bit of kernel development experience knows how to do that. If you don't have a kernel development experience, as you can see, it's pretty easy. So here I'm showing the libmicro HTTPD package. So basically we're defining a config symbol and naming the option. That's what will appear in menu config. Define the dependencies. So here this package has no specific dependencies except that the toolchain should provide thread support, a description, and then we have a little comment that says, hey, your toolchain doesn't have threads, so you can't enable libmicro HTTPD. Once this is done, and obviously this should be done in a directory that's named after the package, so package/libmicro/httpd/config.in. Once you've done that, you need to go to the upper level config.in, which includes all the config.ins for the different packages, and add a new include. So it's source and the name of the file we just created before. So that's the easy part. And then you need to describe actually how to build that package. So how to extract it, how to configure it, how to build it, how to install it. But it turns out that libmicro/httpd uses the autoconf and automake. So the way to build it and configure it is very standardized. So instead of repeating that for each and every package in build root, you can use what we call a package infrastructure, which is named AutoTools package, and which is going to factorize all the gory details of building an AutoTools package and do all of that for you. So what we have to do here is just give a bunch of variables, values, the version of the component, where it can be downloaded from. We can also give the license. I'm going to get back to that later. We are saying that it should be installed to staging. This means that it's going to be installed both in the target and in the sysroot of the toolchain because it's a library. So if we want the cross-compiler to see that library for upcoming compilations, then we need to tell that. And then we can pass configuration options to the configure script. I've stripped down the real thing because here we handle things in the real build root. We handle things like optional SSL support, for example. So if we see that we have OpenSSL available, we pass one more option to tell libmicro/httpd, please enable SSL support. And that's all what you need. That will create the package. It will automatically download the tarball, extract it, it will configure it, build it, install it. So that's all what you need for AutoTools packages. So we have different package infrastructures depending on the type of package you want to create. If your component uses AutoTools, it's AutoTools package, as I've shown. If your component uses CMake, then we have CMake package. If your component is a Python module using either dist-utils or setup tools, we have Python package recently that I've recently integrated. And then for all the rest, we have an infrastructure called generic package where you have to do a little bit more work because you have to explicitly say what should happen to configure and build the package. And what's coming is infrastructure for Perl and Lua packages. So we're progressively improving those package infrastructures to make it simpler to package Perl and Lua stuff. Beyond building the system itself that you run on your target platform, another thing that build root provides is what we call a legal infrastructure. So as you've seen in the example, the libmicro/http package is associated with licensing information, like which license and which file describes the license. And we have that for not yet all of the packages, because that's something we've introduced like less than a year ago. But it's growing, and I think more than half of our packages have licensing information. So what we can do is that when you run make legal info, it's going to extract the legal information for all the packages that you've selected in your embedded Linux system, and it's going to provide you a licensing manifest in a CSV format, saying all the components, all their version, all their licenses, so that you can very easily do licensing compliance. It's going to store in one directory the license for all the different components and the source code for all the different components. So if all of this is right, technically you can just take all that stuff, put that up on your website, and you should normally be compliant with the open source licenses that you use in your system. At least that's the idea. So I think that's a pretty cool feature for companies doing embedded Linux systems. It uses directly the embedded Linux build system tool to help in doing license compliance. It can also do dependency graphing, so that's very interesting to understand why a particular component has been taken into the build. So you do make graph depends, and it generates a PDF that looks like that for I think it's the Raspberry Pi system, that's the configuration I was showing before. So I'm not sure you can read, but we can see that there is BuzzyBox, it's building the kernel, and the kernel needs a bunch of things. It's building light HTTPD, which needs some other stuff, and so on and so on. So we can very easily understand why a component has been brought into the build. Another thing that comes with build root are dev configs. So it's pretty much like the kernel ones. Dev configs are configurations for popular platforms. And in build root, we've decided to have configuration that build a minimal system for the platform. So for example, we have configuration for the Raspberry Pi, for the BeagleBone, for the QB board, for Panda board, for many Atmel boards, Freescale boards, and also for many QEMU configurations, so that you can like experiment with build root and run things in QEMU ARM, QEMU MIPS, QEMU Spark, and we have many of them, like tens of them. And it builds the most minimal system possible. So like the 2 megs root file system I was explaining before, it is just the C library and BuzzyBox, and that's it. And then on top of that, you can add more packages depending on what you want to do with your system. Some people will use their Raspberry Pi to do a media center. Some other people will use it to maybe monitor the temperature in their house or something. So the set of packages will depend from one usage to the other. But at least those dev configs, they build the right kernel, the right bootloader, select the right architecture options, and so on, and give you a system that is known to boot on this platform. So to use them, you just do make blah blah dev config. So like make Raspberry Pi dev config. It's going to load that default configuration, and you start the build by running make, and it's going to produce you a system that runs on your Raspberry Pi. As I said before, build root is an active project. It has had a quite hectic history with periods of without any maintainer, things going quite bad and so on. But since 5 years now, it's since beginning of 2009, we have a maintainer, Peter Korsgaard, who lives in Belgium, and he is the gatekeeper for all the changes going into build root. So a bit like in the Linux kernel, there's only one person having commit access to the Git repository. We review patches on a mailing list and so on. So since he has been leading the project, we have published releases every 3 months, very regularly. They have always been in time, so it's pretty good for users to know that, well, every 3 months we care about stability. So we basically have 2 months of development and then 1 month for bug fixing. We have a growing number of contributors. These days we have between 35 and 40 different contributors each month that have patches integrated into the tree. So we have in fact many more contributors sending patches, but for the patches that are accepted, it's like 30, 40 people each month. Mailing list activity is also showing that the project is gaining interest, like between 1,500 and 2,000 emails a month, and it's growing. And the number of packages is also growing. So as you've seen, it's been flat for a while, which was several years ago, because we have had a huge period of cleanup when the new maintainer was, appointed. And we cleaned up a lot of things, like rewrote most of it. And now we are in a phase where we can benefit from the cleanup and add many more packages, which is what's happening right now. And we have physical meetings twice a year. So here it was last year, February, in Brussels, in the Google offices, because since they use Buildroot, they are nice enough to provide us meeting rooms. And so we have like developer meetings, and we're going to have again one in Google offices in Brussels just next month, in early February. So if you want to try out Buildroot, there is a pretty good documentation, as I said, that's available, especially describing how to add packages. It's very describe things with a lot of details. And like any other good open source project, we have, as I said, the ugly logo, but we also have the mailing list, the RC channel, a bug tracker. I'm tempted to think that our community is quite friendly and welcoming. I mean, since it's a tool that's pretty easy, a lot of the people that come in are usually newcomers in the embedded Linux space, and we try to be nice with them and explain them how things work and so on. And there are also companies offering commercial support around Buildroot. So to conclude and leave some time for the questions, I have like 8 minutes. I think it's a nice tool, and because it uses well-known technologies and languages, you don't have to learn some funky language to use it, and the community is active and friendly. It's simple. If you want to understand what Buildroot does, it's just a few hundreds of lines of code to understand. They are not the easiest part of Buildroot indeed, but the core of the package infrastructure is really just a few hundred lines of code. So even newcomers, after just a few months of like playing around with Buildroot, they are able to provide patches that touch the core of Buildroot because it remains simple. And that's something that is really key in the project. Whenever we have requests from users for new features, we always try to see whether the request for that feature fits in the simple model that we want to keep, and whether it shouldn't be handled as like an external script that should be called or something like that, to avoid cluttering the tool with more and more use cases that are being handled in bizarre ways. So we try to have like one way to do things and only one, and not clutter with many features. So sometimes it's a little bit to find the right balance here. But I guess it's a challenge that many open source projects are facing. So it's really easy to get started. In just an hour, you can have built your file system for the Raspberry Pi or any other board that's supported and run it on your platform. So it's really easy. And it's pretty efficient. The build times are quite reasonable, as I've shown. Just use a reasonable machine. If you use like VirtualBox on a very crappy machine, of course it's going to take a while, but other than that, it's pretty efficient. Okay, I guess it's time for questions. If you ask questions, please speak clearly and loudly. I'm not a native speaker, so if you like grumble, I'm not going to understand. Yes, please.
I wanted to ask how many lines of configuration you used. It showed 2 examples, and I'm wondering how many lines of configuration did each of those 2 examples require?
So the true real world, so the question is how many lines of configuration each of the real world examples I've shown required? Is that your question?
Yes.
So if you take a .config, it contains many lines of code because it has the value for each option, just like in the Linux kernel. The one I've shown is the result of running make save defconfig, which creates a defconfig file that only contains the option for which you've chosen the non-default value. Okay, so that's what makes them relatively short. For those systems that I've shown, basically just count the number of words, more or less. Like the toolchain is going to be one option, Linux kernel is going to be maybe 5, 6 to select the right version and config, BusyBox is one option, Drawbear is one, Qt is a bunch more, like maybe 5, 10 options. Each of zlib, libxml2, logrotate, ppbds trace are going to be one option each. The Qt application is one. So as you can see, it's going to be maybe like, I don't know, 30, 40 lines or something like that. And this one is a little bit bigger because it has x.org, but it's going to be maybe 60, 70 lines of code of config, but you don't write it. I mean, nobody writes, well, I do write them from time to time, but nobody writes that thing. It's generated by menu config. So you just navigate in the menus here and select whatever you want, just like when you configure your kernel, and you don't have to worry about it. Okay, so the question is, well, first, thanks for thinking the tool is great for newcomers. And the question is there a to-do list? Yes, there are different opportunities for newcomers to do things. We have a wiki on lnx.org for Buildroot, and it has a small to-do list. It's not that big, but it's, well, quite, it has a few things. We have reports from the previous meetings that always list a huge number of things to do and report the discussion that we had. So for newcomers, it's a good way of like seeing what are the topics currently in discussion and maybe jump in some of the topics. And then we have all the patches are recorded in a tool called Patchwork, and it's anybody can look at them and maybe grab one of the patch, test it, review it, and give feedback. That's something we're missing quite a lot at the moment, review of patches. And then we also have a bug tracker, but it's probably a bit trickier for newcomers to directly tackle bugs. And then, as usual, just scratch your own itch and build a root file system for your device, do things, and you'll probably figure out that something should be updated or improved and things like that. Other questions? Yes, please.
The recipes for the individual packages look very much like ports. Like the BSD port system, it's a fragment of a makefile with an include. I'm wondering if you can't steal from the various port systems or Gentoo with respect to building a new package that is currently in the system.
So I'm being told that the recipes, like the makefiles, look very similar to the ones of the FreeBSD ports or Gentoo recipes and so on. Yes, and that's the same for other embedded Linux build systems. I mean, if you look at Yocto, Open Embedded, PTXGist, and so on, they all have this kind of recipe language. And we don't directly reuse what the others are doing, as we don't copy-paste what they're doing, but we look a lot at what others are doing. And I believe they're doing the same because I know some other build systems are reusing some of the patches that we have and so on. So there's a lot of reuse, but it's not direct reuse because the syntax is different. The variable names are different and so on, but there is a lot of reuse. I mean, I'm currently working on improving the Python cross-compilation support. I'm talking with a guy from Canonical doing work on Python in Ubuntu, and I'm interacting with other build systems, also cross-compiling Python. So we are interacting with other projects, but it's much more difficult to directly reuse recipes. So the question is between internal and external, what should I choose? Internal seems to take quite a while to build. So yes, indeed, internal is going to build binutils, then going to build all the dependencies of GCC, then gonna build GCC like 3 times and build the C library, so it takes a while. On my side, I mainly use external toolchains. Some of them I produce with Buildroot itself. So I use Buildroot once to build a toolchain, and only that. I keep a copy of it somewhere, and then I use that toolchain as an external toolchain in Buildroot, and I have a good number of them for each of the architectures that I care about. So that's typically the way I do things. But I know some people stick with the internal toolchain because they don't rebuild it every day. You build it once, and then you do more modification to your configuration, and only maybe at night you're going to restart the build from scratch. So, of course, yes. Whenever you do a make clean, it's going to rebuild everything. So you'll have to rebuild the toolchain again. So Buildroot has a very simple approach to configuration changes. It simply doesn't track them. So when you do a configuration change, if you add a package, it's going to notice because, well, it's not installed, so it should be installed. But if you remove a package from the configuration, it's not going to remove it from your target root file system. Other systems do that. We don't do it simply because it would add too much complexity to the core. Last question in the back.
Can I use Buildroot without a network connection?
So the question is, can I use Buildroot without a network connection? I will say yes. But at some point, you will need a network connection to grab the tarbles once. But we have a lot of mechanisms to help you do offline builds. So we have make source, which is going not to trigger the build, but only the downloads of each of the tarbles that are needed. We have make external depths, which is going to spit out the list of the tarbles that you need to do an offline build. We store all of the tarball in a specific location, but you can also give what we call a primary site, which is an HTTP server where Buildroot will fetch tarballs instead of going to the web. So like in your company, you can have one internal HTTP server with all the tarballs that you care about and be completely isolated from the rest of the world. So that's a pretty common requirement in some companies. So I think we support that quite well. Well, okay. Thank you very much for your attention.
Hey, what's going on, guys? In this video, we're going to cover the top 10 Linux interview questions. These are the most common Linux system administration job interview questions that you'll find out in the wild. So these are what you'll get in your first phone screen generally. There'll obviously be maybe more specific interviews after this, and it also depends on the position you're actually interviewing for. Any given position might involve lots of other tech too. While this covers the majority of like the types of things that are asked during junior Linux sysadmin interviews, you may also want to know sort of the similar types of questions for databases, TCP/IP and networking, programming, or a specific programming language. There may also be infrastructure or architecture questions if you're doing a more mid-level or senior type position. Likewise, you may be asked about specific applications or services. You can get mad, you can get sad, you can have lots of opinions about this. Whatever. This is just the reality for tech phone screens. Your interviewer only has a couple of minutes to figure out if you're worth more time investment. So really, regardless of what kind of job interview you're preparing for, if it involves Linux in some capacity, you should be really comfortable with these basic things. If you haven't yet, make sure to check out my basic Linux system administration playlist, because it covers sort of a lot of the theory and a lot of how Linux works behind what we're going to talk about. As a last piece of caution or word of advice, do not just memorize these things, because even if you make it through the first phone screen, they're going to be pretty pissed if it turns out that you actually don't understand what you're doing after you make it through by memorizing answers to these basic questions. Use these questions as a jumping off point for further exploration. Okay, so let's jump right in. The first question you should immediately know the answer to is, how would you check the kernel version of the currently running system that you're on? The answer is uname. Uname prints out system information. Specifically the -A, the A flag, uname -A, will give you everything it's got. So you've got your host name, OS, kernel, release, kernel version, architecture, etc. There's a couple small permutations of this that you can use. So kernel version and kernel release, if you're looking for just those specific chunks of information. But that's uname. So if someone asks you, how do you check the kernel version of a system, or even what operating system is it running, this is a fairly quick way to find out. Another favorite question is, how would you go about checking what your current IP address is? And this may come in a couple permutations, like, oh, what's the current address on, the ETH0 device, or what's your current IPv6 address, or what have you. There's a couple ways to do this. I'll show you sort of the old and the new way. The old way is if config interface configuration. I've got a bunch of little devices here. Don't worry about that. This is the loopback device, and this is our Ethernet device. And you can see our IPv4 address is here, along with broadcast and subnet mask. Our IPv6 address information can be found here. Now, if someone asks you for a specific interface, in general, you should be using the newer IP tools command. So IP adder, we want the address, show, that gives you everything. so all of your devices, or you can give another argument the device name. So IP adder show 0. As you can see, that gives you all the info for Ethernet 0, including IPv4, insider notation. How would you check for free disk space? Other versions of this question are, how would you check how much disk space is left, or what percentage of disk space you're using? Don't get tripped up by different ways of asking these. DF is your friend. DF, all file systems, human readable formatting. So DF space dash AH. This will give you a readout of all of your file systems, including virtual file systems. You can see our hard drive partitions are here, and our root partition is mounted on SDA1, and you can see it's 5.8 gigs of capacity. We've used 5 gigs of that, so we've got about a half a gig left. We're using 91%. So DF, remember that, disk-free. Managing services is a completely normal part of being a Linux sysadmin or working with Linux in general. So don't be surprised if someone asks you, how would you see if a service is running? Or how would you start or stop a service? Or how would you reload a service? On any newer system, most major Linux distributions have switched to systemd. However, on an older system, you would have said either service, I'll use udev just as the service name. This might be nginx or MySQL or what have you. Service name goes here. Service udev status checks status of a service, start, stop, etc. are also arguments you can put at the end. So service, service name, and then what you want to do to it. On a newer systemd system, so something that is not running sys5 init or upstart or another init system, you would use systemctl. This is the new version, quote unquote, if that's all you remember. Systemctl status service. Now, I'm on an old system. I'm not using systemd, so this is a command not found. But the important thing is it's systemctl status service name. You'll notice that this is actually reverse the order of the service or unit name argument. Systemd calls this a unit instead of a service. But that's pretty much all you need to know. It takes the same start, stop, enable, disable, reload, etc. You can see I've got some files and directories here. How would you check the total size of everything inside of a given directory? I'm going to say dush code. We'll check the code directory. Disk use, du. This is going to go and tally that up. So you can see I've got 80 megs worth of stuff in my code directory. Nice and easy. A little bit more networking focused. How would you check for open ports, let's say? This question can be asked in a couple different ways. Check listening network sockets, open ports. You could say services that are listening on TCP or UDP ports or sockets. So this question can come in a couple different versions, but if you hear, network socket, listening, ports, TCP and UDP services, start thinking netstat, because netstat is what shows you that stuff. So by default, it gives you basically uselessly big output. It's meant to be filtered down with other Linux and Unix tools. So you'll probably want to run something like netstat. I like TU, so for TCP and UDP, LPN, listening, tulpan. Just remember that, and it's pretty good shorthand for like most times when you need this. Obviously, man netstat will get you the manual page for netstat. More on that in a second. So this shows you the address and port that different things are listening on. I'm actually going to run this command as root because you'll see in a second, you can see on the right this PID or program name is actually blank for everything because we're not root. Only root can see that. So if we say sudo that, so execute it as root, you can see we now have all that extra information. Okay, so from left to right, what type of service is it? Well, it's TCP, IPv4, TCP, IPv6, UDP, UDP, IPv6. Excuse me, getting a little excited here. The local address that it's listening on. The 0000 means all public addresses. Port 80, foreign addresses. Is it listening? And the process ID and name of the process, so it actually sort of looks up the process name from the PID that owns this socket. So you can see Nginx, our web server, is listening on port 80, and anyone on our local network that can get to our machine can check out what we're hosting on our web server. 127.0.0.1 is our local machine here, so this is actually not accessible from outside of our machine. Again, for more on that, you just learn a little bit more about networking, but this netstat-tulpn is extremely useful, and again, remember to run it as root if you can, because it just gives you that extra, okay, who is actually listening on that port is very interesting to know. How would you check CPU usage of a given process? You can run ps aux and then grep for your process name. This is a pipe. If you're not familiar with pipes, I highly suggest that you watch some of my basic shell videos. It's like a building block of Linux, and you should not be a sysadmin if that doesn't make sense to you. So ps aux, pipe it into grep, and look for Nginx. You can see these are all the processes right now in the process table that have Nginx in the name, and you can get some process information this way. The user it's running as, you can see the master process is running as root, the worker process is running as data, etc., etc. You kind of need to know how to parse this. Read up on PS. Another way of doing this is top. You'll find top just about everywhere. So this is updated by default, I think, every second or 2 seconds. This gives you a lot more information, top. You can see by default it's ordered descending order by CPU time, percentage of CPU that it's using. So this will be updated with your most CPU intensive processes, although you can change what it's sorted by. Likewise, it also gives you a bunch of other stats about memory, swap in use, load averages, etc. A nice alternative to this, although you won't find it installed by default, is htop. If that's interesting to you, I like this. You can search it easily with like the slash key, search for some process. Gives you a nice little graphical representation of the cores it sees, memory, swap, etc. Nice and intuitive. So that's how you sort of check what's going on with processes, what users own a process, what a process is running as, and things like CPU, memory usage, etc. How would you mount some kind of new volume? Let's say a new hard drive partition that you've just plugged in. Let's say a USB stick. How would you mount that in your system? Well, Linux will generally have a directory called mount on root, and that is sort of the canonical place to mount things. So to mount a new volume, you would say mount is the command, and then the absolute path to the volume. So if it's a device, like let's see, it's a hard drive partition, SDA2, it's the second partition on the SDA hard drive, you could say mount, address, and then the mount point. If I just wanted to mount it on mount, MNT, this would be the command. Likewise, checking for existing mounts is just the mount command without any arguments. So you can see here's what's mounted and the mount options it's got. And you also get file system type. So ext4, got a btrfs here, on and on. Last little trick on mount, just because it's fast. If you automatically need to mount a volume at boot, what file would you look in? The answer is etc fs tab. If we take a quick look at that file, you can see this is our disk partitions that we want. So this is SDA1 and its UUID, unique user ID, unique device ID, and our swap partition SDA5 with its unique ID, so that we can find that at boot time. When I generally make changes to config files that are not part of a larger system, like just on my desktop, so not as part of a business configuration management setup, I like to just leave my name in there just so I can quickly grep for files that have this string in them. so that I can see everything that I've changed on a system, that isn't in some kind of configuration management or automatic provisioning script. Finally, the very, very most important thing, man pages. You will get asked how you look stuff up. How do you find answers to questions? Your first answer to this should be, if it's a command, I look at the man pages, the manual pages. So man command gets you there. So for example, man PS, you want to know all the options you could pass to PS. It's kind of a big command. Here are all the interesting things you can do with it. Generally, man pages have a sort of name of the command, basic synopsis, the way you call it, sort of the syntax for calling it, a description of the command, sort of a mini, very dense tutorial usually, and some examples. BSDs are a lot better than most Linux distros for this, but you hope to find an examples section at the bottom. In this case, you've got an examples section here, although this is often missing depending on what the command is. And then a listing of all the options in detail. You can see this is a very old and well-documented command. Other than man, Google server fault, Stack Overflow, these are good answers in an interview. You should know multiple ways of finding answers to questions. If you haven't read it yet, I will link it here, but the How to Ask Smart Questions or How to Ask Questions the Smart Way article is required reading for anybody in tech. So I hope that's been useful. If you want more of these, either more for Linux, for higher level Linux questions, or for other sort of skill silos like databases, networking, programming, infrastructure, cloud stuff, applications and services, I'd be happy to make more of these videos. So if they're helpful, leave a comment with stuff you'd like to see covered, subscribe for more. And if you haven't already, check out the basic sysadmin skills playlist, because there's just a whole lot of background stuff you need to know in there. So good luck on your job hunt and in your interviews, and maybe we'll run across each other in real life sometime. Thanks for watching, guys.
Greetings and salutations, and thank you for clicking on the video. Today, it's the beginner's guide to the Bash terminal. This is the scariest part of Linux for new users. You don't need to use a terminal to use Linux. Many distributions provide very nice GUI desktops, graphic user interfaces, that give you all of the point-and-click comfort that you're used to. However, in Linux, Bash is a big part of the system. And if you ever run into a situation where you need help with a problem, chances are, if you are working with somebody in a forum or somebody's helping you directly, they're going to tell you to open up a terminal so that they can help you to fix the problem. Also, the terminal is very powerful, and once you learn your way around, you might find that you like working in a terminal better than doing the point-and-click thing, because it allows you to do very complicated things with just a few little commands. So in today's video, I'm going to give you the crash course. This is the beginner's guide. We're going to go through a whole bunch of information very quickly. And the idea here is to provide one video that will help people who want to get started with Bash. There are a lot of great tutorials on YouTube about Bash. Most of them are multi-part series, and they're very long, and they go into a great deal of detail. I myself posted one of those a little more than a year ago. However, this video is a crash course. If you sit down and you watch this video from beginning to end, you are going to have the very basic concepts and tools you need to actually use the terminal, and most of what I'm going to show you is where to get more information. So it's pretty cool. Now you can see why the terminal would be intimidating. When you open one up, all you get is a blinking cursor. It doesn't tell you anything. Well, that's the difference between Bash and a GUI. A GUI interface is one that will give you options. You can pretty much intuitively figure out what you're going to do. In the terminal, when you're working at a command line, it is assumed that you know what you want, and so therefore it doesn't offer a great deal of help as you roll along. Bash assumes that you know what you're doing, so be careful as you roll through, because there are some things that you can do that might damage your system. We'll point those out as we roll along, so pay attention to those cautions. So the first thing that you're going to want to learn how to do is figure out where you are and what you're looking at. So the very first command that I'm going to teach you in the terminal is ls, which stands for list storage. And when you run that command, and you run a command by typing it and then pressing the enter key, it will give you a list of everything that is in the current directory that you are logged into. The directory that you're logged into is usually your home directory. And that is told to you right up front there by the prompt. This is Ubuntu, and this is pretty much the typical prompt that you will get, and it tells you a lot of information. First of all, it tells you who you are, which might sound like something that you should already know, but there are occasions when it's nice to know that information and have it on the screen. And it tells you exactly what computer you're logged into. With Bash, you can use the remote shell or the secure shell, SSH, to log into other machines. So if you have more than one terminal up, it's kind of nice to know exactly what machine you're working in. And then finally, you'll see that little tilde character. Well, that's an abbreviation for your home folder. Tilde always represents your home folder. And finally, the last thing that you see is the $sign. The $sign indicates that you are logged in as a standard user, which means that you have regular privileges. You cannot enter a command here and run it as an administrator unless you preface it with another command or you switch to the administrator's account, which is known as root. So that's what the prompt tells you. And ls tells you what files and directories you have with you. Before we go any further, it's probably a good idea that we take a look at the basic Linux file system so that you can get an idea of what we're dealing with here. This is called a tree. It's upside down. If you turn it right side up, then it would look more like a tree, because we start out at root, and root is the base of a file system on a Linux or Unix machine. And everything is in root, which is usually a bunch of directories. All directories are files that contain more files. So you can have files and directories in the root directory, and then each directory can contain more files. The one that we're probably going to be most interested in is the home directory. That's where all of the users who have accounts on the computer have their files stored. It's in there somewhere, and that will make more sense as we roll along. So ls shows us what we have in the current directory. The next command to know is pwd, where we can print the present working directory. So pwd will tell you exactly where you are. And in this case, it gives us the full path. This is not abbreviated. So a path means that if you go from the root of the file system to wherever you are now, this is how you get there. So in this case, we go from root to home to a directory called Joe, and that is me. Directories and folders, the names are interchangeable. That's something else to keep in mind. You may hear people refer to them as folders. And that is because way back a long time ago in computer science class, when they were first teaching us all about computers, they likened directories to folders in a file cabinet. So the hard drive would represent a file cabinet, the directory would be the folder, and of course files were within those folders. So when you're working in a graphic user interface, usually we call those folders because they're represented as cute little pictures of folders, just to make sure that that's understood. PWD tells you exactly where you are in the file system and gives you the full path. That is called an absolute path. There is also something called a relative path. And a relative path is how you get to something from where you are right now. And it assumes that whatever you're trying to get to is in your current working directory. So in this instance, I could, for instance, type in ls and then type in documents. And I'm going to use a trick that I'm going to tell you about in just a second there to fill that up. And now it will list everything in the documents folder. And I used a relative path. Well, I can also issue this command this way. I can say ls root home Joe, and then I can do doc, type that correctly and it would help. Now I'm going to get exactly the same output, and that is because I used a absolute path. So you need to understand the difference between those two things. So let's clear the screen here, and let's issue ls again, because I want to show you another thing that ls does. And this is another important concept to understand about commands, is that they usually have options. So if I use a dash or a hyphen, and then I give ls the A, it's going to show me everything in the directory, because there's more than what the eye can see. Some files and directories in Linux are hidden, and they are hidden because they have a little dot character in front of them. So there's way more in your home directory than you just see with plain ls. And then ls has more options that you need to know about. So ls, and then the next command would be l. What this will do is it'll give us a long list of everything, which shows us all kinds of information about the directories. If I issue that same command and now I tack A on there as well, now I get everything in the directory. Don't worry about all of that gobbledygook on the screen. We'll talk about that as we roll along, and it will start to make more sense. So ls and pwd, those are the first two commands that you need to know, because it tells you where you are and what you have to work with. The next command that I want to talk about is the change directory command, because this one's really important. This is how you get from one place to the next. So this will also show you the next concept that we want to get into, which is called auto-completion. So let's say that I'm sitting here at my home folder directory, and I want to go to the documents folder. Then I would use cd, change directory, and then I could just type in doc, and it will autofill it for me when I press the tab key. This saves you a lot of typing. Remember that people who work at a terminal, whether they be programmers or sysadmins, they're lazy. We want to minimize our typing, so there's all kinds of shortcuts. In my original Bash series, I didn't cover auto-completion because the old school way of teaching it is that you type everything. But since then, I have rethought that, so that's why I'm introducing that concept. Now, you will notice if I only type do and then hit the tab key, that it doesn't do anything the first time. If I hit it twice, it now lists everything that could possibly be auto-completed. So it'll give you a list of all of the files or directories that you're looking for that you could use. So in this case, well, let's change our mind. We want to go into downloads. So now I type a W, autocomplete again with the tab key, and now I'm in downloads. Once I'm there, if I want to get back to the home directory, I got a couple of options. Anytime you want to go up one level from wherever you are, just put that ... in there, and that tells the system, hey, I want to go one level up. Or in the case of the home directory, I've got the ability just to type cd. So let's go, and we will go into downloads again, cd, boom. Cd with no argument basically tells the system, take me home. And also, there's another way to do this, which is rather redundant, but it's good to know. The home directory is abbreviated by that tilde, so it'll do the same thing. It'll take me home. So that is the basics of how the cd command works, and it's one that you will use a lot because you can move around the system. So let me show you another thing about cd here and auto-completion together, which makes life really simple. So I'm going to go ahead and switch to my documents folder, and now I'm going to list the storage in there. Oh, oops, I forgot to issue the command. Oops. There we go. All right. I'm going to make typos as this rolls along. I make a lot of typos while I'm typing and talking, so please forgive me. It will happen, I know. All right, so here we are, and if I just list the storage in here, and if I scroll up, you'll notice that we have some directories in here that have very long names with spaces and all that kind of stuff. Well, dealing with directories and file names that have spaces in them can be a bit of a pain. So this makes auto-completion really useful. So if I want to cd into a directory I have called bash scripts and guides, notice that it fills that in for me. And not only does it fill it in, but you see those little slashes there, the backslashes. Those are called escape characters. So if you are going to create or access a file that has spaces in it, then you use those to tell the system, yo, ignore the space, act like it isn't there. and that will allow me to get into that directory no problem. Those of you who are already using Ubuntu may notice that my prompt is not showing the full path to where I am. That's a modification that I have made. Ubuntu usually will show you the full path. So on your machine, it may say :documents, and then it would be whatever directory you happen to be in. To get back to the home directory, boom, there we go. Okay, so that's the basics of using CD with auto-completion. One more thing that's related to CD that is very useful. Let us say that you are in your downloads folder. Type that correctly. And you need to jump over to another folder on the machine, which is way somewhere else on the file system. So in this case, we're going to be in etc. Well, you could CD over there, and then you could use a CD command to get back. But there's another way to do this. And the command for that is push D. And then give it your directory. And now what it will do is, you see, it's saying that we've gone to the etc directory into the downloads directory. And I can work here for as long as I like. And then I can use a command called popd, and it takes me back to right where I was. Yes, you could use 2 CD commands. Why is that useful? Well, what if you don't remember where you were? What if you end up working in the etc directory for a long time and you go, wait a minute, what directory was I in? I'm not really sure. Well, if you use push D and pop D in that particular situation, you'll always jump back to where you were and you won't lose your place. You won't have to remember, well, what directory was I in to get that file? Well, there you go. So there you go. That's how you navigate the system very basically. So the next concepts that we want to get into is understanding what we're looking at. So let's do that ls again, and let's give it an A. And, well, let's get into a directory that has something in it. So I'm going to go back to my home directory. We'll go to A, which will show everything. And now you see we have a list here, and we're not really sure what we're looking at with some of these things. Linux does not necessarily need or use file extensions, especially when working at a command line. If you're coming from Mac or Windows, you may be used to seeing extensions on things. Like if you create a text file with a word processor, it may have an extension called doc, or in the case of LibreOffice, it would be ODT. And that's telling you what kind of file it is. Well, Linux doesn't care. It doesn't need those extensions to function. It can figure out what a file is on its own. So the next command that I want to show you is file. So let's say, for instance, we don't know what that little .face file is. All we've got to do is issue the file command and then give it the file name, and it tells us that it's a JPEG image. Well, what about that weird one that's got? Now you notice I'm not going to type the whole thing. We're using auto-completion. Now it tells us that that's a sound file, and as a matter of fact it says it's a WAV file. So file will tell you what you are looking at. Well, let's do that with one more just to prove a point. File, and let's do this thing here called SSR. Well, it's telling me that that's a directory, which means it contains more files. Now in my terminal I get things color-coded, which means that depending on what kind of file you're looking at, you may have a different color. That's very useful. Not every terminal that you sit down in front of is going to give you that lovely option. So it's nice to know how to figure out exactly what kind of files you're looking at, and that is files. So the next thing that you're probably going to want to know is, how do I find a file? I mean, there are thousands of files on this system, and I need to look for a file. Somebody's telling me I need to edit such and such file, and I have no clue where this file is. Well, there's several ways to do that, but the easiest one there is in Linux is the locate command, and it takes file names or parts of file names. So let's say that somebody told you that you had to edit the fstab command or file. You have no idea where this is. If you use locate and then you press enter, it gives us everything that has the name fstab in it. Now you'll notice there are a lot of references to fstab. But the first one is the one we are really interested in, which tells us that it's in etc. And the locate command uses a database to find things. So one of the things that you may have to do if you want to make it useful is update that database. If you just installed Linux like an hour ago and you're trying to do something with the system, chances are locate will not work at all because this database does not exist. What Linux distributions do is they usually set the system up to update the database for locate once a day. So if it doesn't work today, it may work tomorrow. But you can issue that command yourself and then you can update that database. So let me show you how to do that so locate becomes very useful to you. We're going to jump ahead in our concepts here because I'm going to actually issue this command as the super user. I'm going to have root privileges to do this because to run the update db command you have to have root privileges. So if you're working on a computer in a company or at school, you may not have root privileges. You may not be able to use this command this way. You're going to have to ask your administrator, hey, update the database for locate so I can find this thing. But if you're running your own computer, then you should have administrator privileges. So it's sudo update db, and it's going to ask for my password to make sure that I have authorization to act as the super user, and then I get no output. It actually does it. If this command had never been run, it was the first time that you were running it, it may take it 2 or 3 seconds to run. You won't see any output on the screen, but when your prompt comes back, you know that your locate database is nice and ready to go. So the next command that we're going to take a look at is which. And the which command finds other commands for us. So if you know what a command is, but you don't know where it is, or you don't know if it's installed, this is how you can find out. So we will type which, and in this case, we're going to look for a little command called cal, which doesn't do anything but print a calendar on the screen and tell you what day it is. So if I do that, it tells me, oh, yes, it is installed on the system, and it is in a directory called user/bin/cal. Cal is the name of the file. So now that I know that that command is installed, I can run it and it prints me a calendar. It's a very simple command, but it is very useful and it's a good one to know. And the last one that I want to show you is history. The history command shows you all of the commands that you've already typed. What bash does is it keeps track of all the commands that you issue to the system. And you can access that in many different ways. I'm only going to show you 2 in this particular video, but you can always look for more information about that. You can use this in multiple ways. So the first thing that you can do is just use your up arrow on your keyboard, and it will show you the last commands in the order in which you typed them. So you see all of the commands I've used so far to demonstrate are listed here. So if you type a command and then you go, oh, wait a minute, hold on, I don't remember exactly what I typed, then you can just scan up your history and look for that command. You can find it again. Now, if you want to see what is in your history, and you need to find a whole bunch of stuff, then you can just type in history, and make sure I typed it correctly. Yes, I did. And if you press enter, now it lists everything that you've typed in. History usually keeps up with the last 1,000 unique commands that you've typed in. And I'm going to show you a little bit later on in this video how to make this even more useful. So if you don't want to sit there and look at them one at a time, you can just roll up and down, and then you can also issue these numbers in lieu of the command itself. Now if you want to find out how to use that, you're going to use what I'm going to show you in the next part of the video to figure out how to do that. So that is history, and that is how that works. So the next thing that you need to know about is getting help, because there's plenty of help available to you. And I'm only going to show you a few options for getting help. There's a lot. If you're sitting at a terminal and you're trying to figure out how to use a command or how to do something, there's a lot of ways that you can get information without having to go to a web browser, without having to have the machine hooked up to the internet. There is a lot of help information that is already here, and all you have to do is know how to get to it. So the most simple command is what is. So if you want to know what a command does, you just go and what is this? What does it do? Then this will give you a very short little explanation. So we looked at the cal command, which is that calendar command, and it says it displays a calendar and the date. That's it. That's all it does. So what is very useful if you're just trying to figure out what a command does, and there's a lot of information. And then there is another way to find out information about commands that you might not completely understand the syntax. You may want to do something with the system, but you don't know which command to use. So it'd be kind of nice to kind of give the system a pointer and say, hey, I want to do something that involves time, but I don't know exactly which command to use. Well, in that case, you can use apropos. And then we're just going to give it time. Now watch this. We're going to get a bunch of output on the screen. I'm using my mouse, by the way, to scroll up and look through that. And so it shows us all kinds of different commands that are related to things that have to do with time. Very useful. Well, if you need more intense information, the next one to know, and the one that I use more than any other command, is...
So get this. Every 1.23 seconds, a new user goes to Wix.com and starts creating their professional website. That's 7.
Welcome to the tutorials on Linux. This is first of the 18-part video series helping you become a Linux pro. So let's get started. So what is an operating system? Every time you switch on your computer, you see a screen where you can perform different activities.
Another popular file system format is the extended format, commonly used in Linux. Each file on the disk has a data structure called an inode associated with it. The inode is fixed length, it contains the metadata for the file, and it serves as the glue, linking the data blocks together in the right order. It is this gluing function that is the most interesting. The inode stores 15 data block addresses, or pointers. The first 12 of these point directly to the first 12 data blocks of the file. This makes the strategy efficient for small files. The 13th of these addresses points to a block that consists of a table of addresses for the next blocks in the file. This vastly increases the number of blocks that we can use in a file. The downside is that we've introduced a layer of indirection. If this doesn't give the file enough space, then we use this 14th pointer and not one, but 2 layers of indirection, giving us even more space. And if this isn't enough, we have a 15th pointer, which uses triple indirection for more space still. Just like in FAT, directories are treated as files, only instead of mapping a file name to the first file block, they map a file name to its inode. That path for accessing /foo/file.txt would look something like this. We start at the inode for the root directory, and then following its data pointers, we find the data for the root directory. There we find that foo maps to another inode. Following that address, we consult that inode and find the address for its data block. Looking in there, we find the contents of /foo. That's a directory. So it's going to map the file name file.txt to the appropriate inode. And then using that inode structure, we're able to piece together the data that we need.
What are you doing for Waymo, Cruise, and Uber?
Yeah, so what we've done at Scale is built the data platform for AI. So AI is really built on top of data, and these algorithms require billions and billions of examples of labeled data to be able to perform in a safe or reliable way. So
this 22-year-old interviewed me for a full-time position and rejected me. Just kidding. He was 19 when he interviewed me and rejected me. That was 3 years ago, and I was a senior at Waterloo. Well, in my defense, they never actually explicitly rejected me. They just ghosted me after the interview. I'll show you the emails later.
Let's take a look at their old website.
This company used to be called Scale API, and it wasn't focused only on labeling training data. They built an API for human labor.
We're going to go back to August 2016.
Huh. I don't think that's it. Okay, that's more like it. So kind of like TaskRabbit, but without the in-person stuff. So like phone surveys, transcription, e-commerce tagging, some categorization, outsourcing bitch work, essentially. Now they only focus on categorization, aka labeling for model training. So refined bitch work.
Scale was founded by Lucy Guo and Alexander Wang. Man, even his name looks like a startup.
Anyways, back then there were only 2 co-founders and they were looking to hire their first engineer. So I applied. Here's the email exchange we had. Lucy Guo. I actually matched with her on Tinder a year ago. She didn't respond to me, but then again, my opening message wasn't that great. So apparently my resume stood out because I did a lot of different roles, so that's good. As a startup, we look for someone who can wear many hats. Well, that's good. They quickly hit me up with a take-home project. Oh, shit. Well, I mean, it's too late now. The project asked me to create post endpoints for them so their customers can send annotation box requests, aka send images, and then we, or Scale API, will have their contractors draw boxes around whatever they want and then send them back to the customers where they will probably use it for some machine learning model or something. So this project just focuses on this part and the UI for the Scale contractors to actually draw the boxes. Actually, I think I still have the code for this. Let me whip it out. Alright, so here's what I built so that the contractors can use to draw boxes. Alright, let's send it some requests. So here you see there's 4 images or 4 requests that I'm sending. Alright, and then we'll see this. And here you go. So you could see now that you have a few requests, and here you see a picture of a few cows, and here it says you have to annotate baby cow and big cow, and then the instructions it says draw a box around each baby cow and big cow. So that's cool. So I think it's pretty simple. You just, draw them baby cow, baby cow, baby cow. Oh no, that's not a baby cow. So you can exit out, switch to big cow, and then annotate the big cow. And then you can also reset it. You could also say it's broken. I don't know if ever it's broken. And then there's also the urgency here. You could also sort by urgency if you want. So here you go. You have urgency, sort by urgency, sort by date. You could also click another one if you don't want to do this one right now. Yeah, I think that's pretty much it. So let me just annotate this baby cow, baby cow, baby cow, and then mama cow. This will be saved in the database and sent to the customer, and the customer will receive these things. And then you just submit, and then you submit it. And then here's another example. I think this is a picture of a K-pop group called I know it's Blackpink. Okay, I know it's Blackpink. So here it says draw a box around the best Blackpink member, and then the objects is like my bias. Okay, let's see. Okay. Okay. Okay, and then oh shit, are you serious? All right, so I think you get the point. And they also told me to use the mean stack if I can. But to be honest, I wasn't much of a front end guy, so I ended up using the min stack. Very patriarchal of me. I had some Angular, but it was clear that I wasn't really using the framework right. But I mean, they said they loved it though. But I have a feeling they didn't look at the source code until later on when they ghosted me. So no hard feelings though. I mean, I'd ghost myself too. I would have been a trash employee.
What's popping, guys? Here's a day in the life of an early startup employee. So here's me coding right now.
So they invited me for an interview, and Alexander, the CEO, interviewed me. We just chatted, and then he asked me an algorithm question. The question was a find median in a data stream question. He had to give me a hint for me to solve it, so that probably didn't help my chances. And unfortunately, he didn't respond to me after the interview. And then, as you can see, here's my last desperate attempt after a month. Oh no, actually, that was my last attempt.
넌 뭔데 자꾸 생각나 자존심 상해 애 같아 얼굴이 뜨겁고 가슴은 계속 뛰어 내 몸이 맘대로 안 돼 어지러워 넌 한줌의 모래 같아 잡힐 듯 잡히지 않아 넌 쉽지 않은 걸 그래서 더 끌어 내 맘이 맘대로 안 돼 지금 너를 원하는 내 숨결이 느껴지니 너를 바라보고 있어 I'm missing you So tonight won't you set me free Baby 날 터질 것처럼 말아줘 그만 생각해 뭐가 그리 어려워 거짓말처럼 키스해줘 내가 너에게 마지막 사랑인 것처럼 마지막 밤인 것처럼 Love 마지막처럼 내일 따윈 없는 것처럼 I'ma fall in love, baby. You can finna catch me. Give you all of this, baby. Call me pretty and nasty. Cause we gonna get it, my love. You can bet it on black. We gon' double the stack on them. I'll be the bunny and you be my Clyde. Rewrite or die, X's and O's. 시간은 흘러가는데 마음만 급해지지. 내 세상은 너 하나만 missing you. So tonight won't you set me free? Baby 날 터질 것처럼 안아줘 그만 생각해 뭐가 그리 어려워 거짓말처럼 키스해줘 내가 너에게 마지막 사랑인 것처럼 마지막 밤인 것처럼 Love 마지막처럼 내일 따윈 없는 것처럼 One, two, three 새로운 시작이야 절대 뒤돌아보진 않을 거니까 날 너에게 던지면 너는 날 꼭 잡아줘 세상은 우리 걷지 못할 테니까 Like pink in your area Like pink in your Baby 날 터질 것처럼 말아줘 그만 생각해 뭐가 그리 어려워 거짓말처럼 키스해줘 내가 너에게 마지막 사랑인 것처럼 마지막 밤인 것처럼 Love